here are those two examples of related rates questions that I wanted you guys to do. All right, and I know that most of the time you don't, but seriously, look in your book, follow along, because like I said, these are all going to be word problems, and I'm not rewriting this paragraph that's in your textbook. All right, so look at page 183, and we are going to do example 2. Okay, so it says that a pebble is dropped into a calm pond, causing ripples in the form of concentric circles. And they give you a nice picture. All right, so let's think about this. I'm dropping a pebble, right? And you guys have seen this happen. When you drop something into water, all of these ripples happen. All right, and it says that they're concentric circles, meaning that there's a circle inside of a circle inside of a circle. All right, so it helps to draw a picture. So here's my pebble, and there's a ripple, and there's a ripple, and there's a ripple, and there's a ripple. Okay, draw the picture sometime. It helps. Now it says the radius of the outer ripple is increasing at a constant rate of 1 foot per second. All right, so let's make two columns. All right, let's make a what we know column and what we want. Okay, so they're telling me that the radius of the outer ripple is changing. So that means that if I start from my circle and I go out to the most outer ripple, this is changing at a constant rate of 1. If it's changing at a rate, remember, rates of change are your derivatives. So this is my r, and it's my radius that's changing. I know that dr dt, all right, the radius with respect to time is changing at 1 foot per second. So dr dt is 1. All right, it's how, and I'll even write this. This is how the radius is changing with respect to time. Okay, it also says that when the radius is 4 feet, all right, so when the radius is 4, so when r equals 4, at what rate is the total area changing? So we want to know the rate that the area is changing. So I don't want A, I want the derivative of A with respect to T. All right, A is area. Okay, so I want how the area is changing with respect to time. Okay, and well, this now becomes nice because we already know how to do the area of a circle. All right, remember that the area of a circle is equal to pi r squared. Well, I want dA dt, so that means I need to take the derivative of both sides. When I take the derivative of the left, I get dA dt. When I take the derivative of the right, pi is a constant, so it's pi. And then the derivative of r squared is 2r dr dt. And now I can plug in all of this stuff that I know in to find dA dt. So really dA dt is equal to, I'm going to write this as 2 pi because that's like the normal way. My r is 4, so this is going to be 4. And dr dt was 1. Which 2 times 4 times 1, that's just 8 pi. So this is telling me that the area of the disturbed water is changing at a rate of 8 pi feet squared, or square feet per second. All right, so kind of like physics, you gotta have your units on this stuff. Okay, so, and that's about it. So I know that, let's recap. I knew that my radius was changing at a rate of 1 foot per second. And I was finding how fast the area was changing when the radius was 4. And my final answer was 8 pi feet squared per second. Alrighty? And if you followed along in your book, that's exactly what they did. So let's flip. Let's go to page 184. And let's do example 3. Okay, it says air is being pumped into a spherical balloon. All right, they even gave you a picture, but notice it says spherical. So I'm going to be using some formula that has to do with spheres. All right, now I'll draw my picture if we all want us to. There's my spherical balloon. And it says that air is being pumped into it at a rate of 4.5 cubic feet per minute. So if we think about it, the air that's going into it, that's the volume of the balloon because it's filling up this balloon. It's three-dimensional. All right, the hint that is in this is that if you see something measured in a cubic something, all right, a cubic means volume because it has 3 dimensions. And if you ever see something like square feet, square is area because it's 2 dimensions. All right, use the problem to help you out. So it says that the rate that the air is being pumped in is 4.5. So that means the rate that my volume is changing is 4.5 cubic feet. Instead of 4.5, I'm going to write this as 9 halves. All right, remember, I don't like decimals. We want to find the rate of change of the radius. So we want to find the rate that the radius is changing. So that's going to be dr dt. And we want this when the radius is 2 feet. So when r is equal to 2. Okay? So now let's look. If I'm pumping air in here, we already determined that that means I'm changing the volume. So I need the volume of a sphere. All right, the volume of a sphere is the equation 4/3 pi r cubed. All right, and again, volume is in, it always has a cube somewhere in it, all right, because volume is 3-dimensional. But I want to know how things are changing, so I'm going to take the derivative of both sides with respect to time. When I take the derivative of the left, that's just dv dt. When I take the derivative of the right, all right, now don't freak out about all this stuff because 4/3 pi, that's just a constant. So you're going to bring that down. And then we're going to do the derivative of r cubed, which is going to be 3r squared dr dt. And I'm going to clean this up a little bit because this 3 is going to cancel with this 3. And, well, I guess that's all the cleaning up that I can do. So dv dt is now just simplified to 4 pi r squared dr dt. And now I can plug in that stuff that I know. All right, let me extend here. So I know that dv dt is 9 halves. 4 pi is just 4 pi. For r, I want this when the radius is 2, so I'm going to plug 2 in here. And what I want is dr dt. So that's just going to stay. Well, now let's simplify. This is really 9 halves is equal to 8 pi. Nope, not 8 pi. That's really 4 pi times 2 squared, which is 4. Got a little ahead of myself. So this is, why am I all the way over here? So this is 9 halves is equal to 16 pi dr dt. And I will divide by 16 pi. All right, now over here, I can write this as divided by 16 pi. Whoops, put the eraser back down. All right, so I can write this as divided by 16 pi, but remember, dividing by a number is the same thing as multiplying by its reciprocal. So instead of dividing by 16 pi, I'm going to multiply by 1 over 16 pi. It's the same thing. All right, and so when I do that, I'm going to get 9 over 16 times 2, that's 32 pi. and that's equal to dr dt. And that's it, although I should probably put units on this. This is feet, so this is going to be feet per second, feet per minute. Okay, so the radius of my balloon is changing at a rate of 9 over 32 pi feet per minute when the radius is equal to 2. Okay, do me a favor, go on page 185 and look at example 5. I'm not going to do it, but I want you guys to look at it in the book, try and do it, see if you can follow along, see if it makes sense. And we will talk about this more mañana. Hasta la vista.